Hello, am I audible? Hello.
Yes, ma'am, we are audible.
Good evening, ma'am.
Good evening, ma'am.
Yeah, so we'll wait for 5 more minutes and then we'll start. So these are the topics I want to discuss today. Today is the first revision session. So we'll cover the topics from week 5 and week 6.
Hello, ma'am.
Yes, Lakshmi. Hello.
Okay, ma'am. I was checking if something is wrong at my end. Okay.
Okay.
Ma'am, today are you going to cover only 2 weeks?
Yeah, 2 weeks and the doubts related to these 2 weeks, 5 and
Ma'am,
6.
will you solve questions or only theory revise?
Both things. If you have any a specific question which is doubtable or you
Specific
want
questions
to discuss, then we can discuss.
already
Ma'am,
asked, already asked in
other
previous
two
sessions.
subjects?
Sorry, what?
Ma'am, I am asking about other two topics, other 2 weeks.
Yeah, so we have another revision session on Thursday. So
Oh.
there we will discuss week 7 and
Okay, ma'am.
so in between I have one or two questions, some questions are related to these topics. So we'll discuss these questions too. So yeah, there will be some new questions which you have to solve. Not more than 5 or 6. Okay, so let's start. It's already 8:05. So first, let's discuss what is one function and onto function. So I'll start with the definition. So we know what is a function. So what is a function? So a map or a correspondence or a rule, whatever you want to say. So a map F from a set A to a set B is known to be a function if it satisfies two conditions. What are these two conditions? If for every element of A, so for every A in A, there is an unique B in B, in such a way that this function f take A as an input and give us B as an output. Then we say that this rule or this map is a function from a set A to a set B. So here these set A and B are also given a special name. So the set A is known to be the domain of a function and B is known to be the codomain of a function. So what is a domain? So domain means you have to collect all those points where your function is well defined. So you can say that this is nothing but a collection of all points, collection of all real numbers. If we are talking about the function of real number, so collection of all real numbers where our function f is well defined. Well defined means either it will give us a finite quantity or it makes sense. It makes sense means, suppose if you have a function f of x which is the under the root of x, right? So we know that this function does not make sense for negative values, because we know if you put x is equals to -1, then this under the root of -1 is not a real number. So that means for negative values, this function does not make sense, or it is not well defined, because it is not giving us the real number as an output. So that's why, what is a domain? So domain is nothing but we have to collect all those real number for which our function is well defined. Well defined means either it will give us a finite real number or it makes sense. For example, under the root of x function. Now, what is a codomain? So codomain could be any set into which our function is mapping. So that means codomain could be the any possible output set. Okay. So for example, if you consider this function under the root of x function, now here f is a function from the positive real number r plus 2 real number. So here this real number is a set of codomain. Okay, so codomain is nothing but any possible output set which contains all the possible outputs of our function. Now here we also define one more set which is known to be the range of a function. So what is the range of function? Range of f. So it's again a subset of codomains. So subset of codomains mean it will collect all those output points. So it will collect all those y belongs to b for which we have input. So all those y belongs to b for which there is an x, for which there is an x belongs to a or a belongs to a, such a way that this function takes this a and map over and give us the output to be equal to y. So ultimately, what is range? So range is the precise output set. So that means you have to collect all the points which can be your output, right? So this is known to be a range of f. Now here, let's take the same example. F of x is equals to under the root of x. F of x is equals to under the root of x. Now we know that if you take any real number, so then this under the root of x is always a positive quantity, right? Positive real number. Because you know the graph of under the root of x will look like something like this. Okay? This is the graph of under the root of x. So that means it is taking all positive y-axis to be its range. So here, in case of this function, y is, f of x is equals to under the root of x, we have domain of function to be equal to all positive real numbers. Codomain of function, since it is defined from real number to real number, that's why the codomain of function f is nothing but all real number. And the range of f is nothing but again all positive real number, because no, whatever input you will take, you will get another positive number only, because under the root function is a positive function. Okay, is that fact clear? I mean, is there any doubt in domain, codomain, range, or the definition of function? Anything which is not clear? Okay, fine. Now let's go to the 1-1 function. So what do we understand by 1-1 function? So 1-1 function means for unique output, I mean for two distinct input, we should get two distinct outputs. So that means, so again, suppose you have a function f from a set A to a set B, and if you take two distinct input, that means x1 not equals to x2, then it should imply f of x1, that is the output with respect to x1, and f of x2. So these two outputs should be not equal. So that means for two distinct input x1 and x2, we should get two distinct outputs, f of x1 and f of x2. Okay, so if these two are not equal, these two should not be equal. So then we say that our function is a 1-1 function. Now there are several ways to find out that given function is 1-1 or not. So first way is this particular definition. So if you have any two distinct input and it is implying that f of x1 not equals to f of x2, then that is our 1-1 function. Now, second definition is just do the negation of this particular statement. Okay, so if we do the negation of this statement, it will say that if you take the same input, f of x1 is equals to f of x2, it should imply x1 is equals to x2. So that means with respect to a same input, we should not get two different points. So if we have a same, if we have a one output, then this output should map to one unique input. Right? That's the meaning of 1-1 function. So we are just taking negation of the first thing. So you can also use this statement and prove, so if this is your hypothesis, then if you are able to imply x1 is equals to x2, then you can say that that function is 1-1 function. The third is just by counter example. So counter example means if you find two inputs which are distinct but the respective output is same, then such function are not one-one function. For example, in case of f of x is equals to x2. Here, if you take x1 is equals to 1 and x2 is equals to -1, then we know that f of 1 is also equal to 1 and f of -1 is also equal to 1 because it's -1 square, so it is equal to. So here what is happening? X1 is not equals to x2, but it implying f of 1 which is equal to f of -1 which is equal to 1. Right? X1 is here 1 and x2 is -1. So for two distinct input, we are getting the same output. So this is not the definition of one-one function. So it implies that f is not a one-one function. Now the last method is the horizontal line test. So what is the horizontal line test? So in horizontal line test, if we have a graph of function and if we draw several horizontal lines, so then the condition is that every horizontal line should intersect the graph at most once. So for example, suppose you have such kind of graph. Now here, if you draw this horizontal line, then that horizontal line is intersecting graph at most once. I mean, it intersecting at only one point. But if you draw this horizontal line, then what is happening here? This particular horizontal line, suppose y is equals to 2 is here. So then this y is equals to 2 line is actually intersecting our graph 3 times. So that means what is happening for this input point, suppose this is x is equals to -2. For this input point, suppose this is x is equals to 1. And this for this input point, suppose x is equals to 4. So what is happening? If f is a function related to this particular graph, now here, since this horizontal line intersecting our graph 3 times, it will imply that what are the coordinate of this point? So coordinate will be -2, 2, right? Because the line is y is equals to 2. So similarly, the coordinate here will be 1, 2, and here will be 4, 2. So that means for three distinct input, which are -2, 1, and 4, the value of function, which is f of -2, f of 1, and f of 4, are nothing but equal to 2. So that's why it will show that this is not a one-one function. So we can say that f is not a one-one function. So if you have a graph and if you draw several horizontal lines and if those horizontal lines intersect your graph at most once only. So it is possible that at some point it won't intersect the graph. For example, or suppose this graph is growing here from constant onwards. Then if you draw a line up here, then it won't intersect our graph. So that's fine. That's okay. But it should intersect at most once only. Then only we can say that our function is a one-one function. So if any horizontal line so the equation of any horizontal line will be equal to y is equals to b for some b. Okay, so if any horizontal line intersect the graph at most once, then f is a one-one function. Okay, so this is known to be the horizontal line test. So these are the ways for judging a function is one-one or not. Okay, and the most easiest one is just the horizontal line test. So that's the reason. So if you know how to draw a graph, then you can actually judge the nature of function as it is one-one or onto. It's very easy to judge. Now let's go to the onto function too. So what are the onto function? Onto, or it's also known to be surjective function. Okay, so onto function means if your range set is equal to the codomain set. Okay, so suppose that's also we can define as, so suppose you have a function f from a set A to a set B, then we say that this function is onto function if for any B, so if you choose any B from this set B, so suppose this is your set B, so if you choose any point B here, so that means for any B belongs to B, there is an A belongs to A, such a way that this map will take this A to this B. So that means for any B, there should exist one A in a domain set in such a way that F will map this particular A to B. So if this condition happens, then we say it is an onto function. Onto function means every image or every output should have a pre-image, right? So whatever A is here, so A is known to be a pre-image of B. So that means every output point should have a pre-image. Okay, so that's the meaning of onto function. So let's observe what if we have a graph, then how we can judge. So suppose you have a graph looking like this, right? So it's nothing but just a parabola. So now here you observe that how we can judge that this function is onto or not. So what we will do, we will look for those y values for which we don't have any input. So for example, if you look this y value, suppose this is y is equals to 2 again. Now for this y value, I have two input points. So because if you draw a line here, it will intersect our graph twice. And if you compute the coefficient of this point, so suppose this is some x is equals to a and x is equals to b. Now the coefficient of this point is a comma 2 and the coefficient of this point is b comma 2. So that means for these two values a and b, our output is 2. So that means for a and b, f of a is same as f of b is same as 2, right? Because this is the graph of f. And we know that any point on the graph will have coordinate x comma f of x, right? Where x is the input and f of x is the output. So similarly, since the coordinate here are b comma 2, so b will be input and 2 will be output. So that means for this y is equals to 2, we have two pre-images a and b. But if you consider some y here, so let's name it to be y is equals to minus 10. Then if you draw a horizontal line here, then this horizontal line is not intersecting with our graph. So that means for this y is equals to minus 10, we don't have any input point. Or for this y is equals to minus 10, we don't have any pre-image. So here, for y is equals to minus 10, we don't have any pre-image. And which will imply our function f is not on. Yeah, it's not on. Now let's take an example of function which is onto. So consider a graph something like this. Okay. Now can you say is it a onto function or not?
No, ma'am.
Are you sure it is not onto? Because it's
Yes, it
growing
is
from
onto.
here, it is minus infinity and growing here is
That's
plus infinity.
infinite.
It will be onto, right?
How?
See, if you take any point, so suppose you'll take any point here. At any point, because it's growing to infinity. So at any point, if you draw a horizontal line, it will intersect to a graph. In the plus, I mean positive y-axis also, and negative y-axis also, if you take any point, then it will also intersect our graph. So that means for any y, we are getting some input x. Correct?
Yes, ma'am.
So that's the definition of onto. Na? So onto means what? For every output element, we should get an input element. So here output or the, you can say image is y and the pre-image is x. So x is input, and if you place x to be input, you will get y as an output. Is that fine?
Yes, ma'am.
Now, can you judge is this function is 1-1 function or not?
No, ma'am.
No, ma'am, it is not 1-1.
Correct, it is not 1-1. Because if you draw a horizontal line here, then it will intersect 3 points. And that's the note. And for, see, what is a bijective function? So bijective means 1-1 plus onto. Now, since this function is not 1-1, so that's why it's not a bijective function. So for bijectiveness, you have to consider two cases. I mean, 1-1 function, it should be a 1-1 function and it should be an onto function. And how to look via the graph for these two functions, we just. Now I'll take one more example about this, but before that, let's try to understand some of the graph. So that means if you have a graph of a function f, then using that particular graph, how can you draw the graph of other functions? Other function means how to draw the graph of its inverse, how to draw the graph of its modulus function, and some adjustment. So suppose, and there are several rules for that. So suppose f is a function from a set A to B, then, so first rule is this is for f inverse. So the graph of f inverse is
Should be
just
a reflective type.
just a mirror image about the line y is equals to x. Just a mirror image about the line y is equals to x. Okay, so I'll demonstrate all these points using Desmos. So for just time being, just know the rules. Okay, so first rule says if you have a graph of a function f, and if you want to compute the graph of its inverse, then that graph is nothing but the mirror image about y is equals to x. Okay, now second function says that if you have a graph of f, then the graph of modulus of f is the here we have to take all the negative parts, negative y values into positive x-axis. Okay, so this will demonstrate by this. Okay, so suppose we have some polynomial, so we can take any polynomial. So suppose this is x to the power 5 plus x to the power 4 or we should give some coefficient here. So like yes. Suppose we have this kind of graph. So suppose we have this graph, this red one. Right now here, can you tell me, is this a 1-1 function or not?
It's not the 1-1 function.
Right, it is not a 1-1 function, because if you draw simply a line y is equals to 5, it will intersect our graph at 3 points. So that's why it's not a 1-1 function. Is it a onto function?
It's one.
Yes, ma'am, it is on
Yes,
to.
ma'am, it's on to.
It is onto function because it's growing here to minus infinity and it's growing upward to plus infinity. So that's why it is an onto function. And now, how can we see the graph of its inverse? Now, since we know that it is, but since it's not a 1-1 function, so that's why it's not a bijective function. So that's why its inverse does not exist. So the graph of its inverse does not exist. But for that, we will take another graph whose inverse exists. Okay. So now, for time being, suppose I have to compute the graph of its modulus. Okay. So suppose I'll shifted this graph by something. So suppose this is our function and we want to compute the graph of its modulus function. So see what happens. All this, whatever these edges are here, now which are lying over the negative y-axis, it will get reflected to positive y-axis with the corner at these points. So let's see what happens. This green one is a graph of this modulus function. So whatever this here, that means whatever edges are there in the negative y-axis, it got shifted to a positive y-axis with the corner at this point, with the corner where we have modulus values becoming 0. Okay, so that's how we can compute the graph of a function, graph of the modulus of any function. So suppose you have any function and you want to compute its graph of its modulus. So what you have to do, you have to take all those values which are situated over the negative y-axis and get reflected over the x-axis. So because here if you put a mirror, then you observe that these all values, whatever are negative in here, they are all shifted to positive y-axis with the corner at this point. Okay. So this is the one thing I want to tell. And similarly for for inverse function too. So we know that e to the power x is graph. E to the power x is an bijective function, which we see in a few times. So what is the inverse of e to the power x is ln of x. So here you observe that inverse of e to the power x is ln of x, and that's why this green graph is actually a mirror image of this red one graph about this slide, about this violet line. So that's how we can compute the graph of inverse function if we have a graph of f. Okay, is that clear? Both the top points?
Yes, ma'am.
Yes, ma'am.
Fine. Now let's
Hello,
go to
ma'am.
the next topic.
Hello, ma'am.
Yes.
Ma'am, what was the reason that you shifted to different inverse function?
Actually, that function is not a 1-1 function, correct?
Okay.
For a inverse function, we need function should be bijective. So bijective mean 1-1 plus 1-2. So that function is not 1-1, so it cannot have an inverse.
Okay. Thank you.
Okay, fine. So now let's go to the next topic. So we have covered so far. So let's go to the composite function. So what are the composite function? Composite function means if we have two function and if you want to apply these two function in a sequential manner. Sequential manner means, so suppose we have two function f and g. So let's be precise with the domain code. So suppose f is a function from a to b and g is a function from b to c. Then we can actually define what is g composition of f of x. So g composition of f of x will be another function from a to c in such a way that g composition f of x is defined by, you will apply g on the value of f. So that means g of f of x. So that's how we define composite function. Now we can also define f composite g with respect to the domain. So suppose I have two functions, then what will be f composite g? So f composite g will be equal to f of g of x. Okay, so this is the basic definition of composite function. So here the main problem is to find out the domain of composite function using the domain of f and using the domain of g. Okay, so let's try to find what will be the domain of f of g of x. Okay, so what you have to do, what do we understand by domain? So domain means all those points where our function is well defined. Well defined means either it will give a real number or it should make sense. So now here, what is happening? So x is our input point, right? So on x, first we are applying g, right? First we are applying g. So that means this g of x should make sense. So what does it imply? It simply implies this x should belongs to domain of g, right? Because if you want to compute f composite g of x, so that means we are applying g first on x. So if we want to apply g on x, then g of x should make sense. And what does that mean? So it means that x should come from the domain of g, right? Now, further what we are doing, we are applying f on g of x, right? So what does it mean? So it means that f of g of x should make sense. So f of g of x should make sense means this g of x should belongs to domain of f, right? So overall, what we can say, so we have to collect all those x which are actually a part of domain of g in such a way that if you apply g on that, then that should belong to domain of f. Now we can actually rewrite this particular scenario using two steps. So first step is you have to find domain of f and domain of g. So what are these two sets? First thing we have to evaluate. Now second thing what you have to do, you have to remove all those points, all those x belongs to domain of g, because ultimately what we are doing, we are considering x from domain of g only. We have to collect all those x from domain of g only, because first we want that g of x should be well defined. So what we have to do next? So we have to remove all those x from domain of g, for which if you apply g on it, for which g of x should not, for which g of x is not a part of domain of x. Okay, domain of x. So either you will remove all those x for which g of x does not belong to domain of f. Because if g of x does not belong to domain of f, it simply implies that we cannot talk about f of g of x. Correct? Because we can talk about the value of function only at its input points or its domain points. So if g of x does not belong to domain of f, so that means we cannot calculate f of g of x. So that's how we can compute the domain of f composite g. Right? So this is a process for domain of f composite g. Now let's try one example. So find the domain of f composite g, where we have two functions, f of x to be equal to 4 minus x square and g of x to be equal to 1 by x square. Again, I'll tell, don't just find out the expression and then find the domain, because it can happen that you will leave some of the points. So this is the one warning we already discussed when we discussed this week 5. So if you want to find out domain, you have to follow these two steps. If you just go by the expression, so that means first finding out F composite G and whatever expression you will get, and then you will compute its domain, then in that case you might miss some of the points. So that's why whenever you have to find out the domain, just go by these steps. Okay. So suppose I'll just modify it. Suppose you have square here too. Okay. So now you have to find the domain of both of the composite function. Okay. So find the domain of F composite G and G composite F, where these are the functions. Okay. So I'll give you 5 minutes and then we will discuss this. So it's 8:33 to 8:40. And please answer in the chat box. Okay. Don't shout it out.
Hello, ma'am. Hello.
I think
Yes.
ma'am is on break till
Yes,
it.
Roshni.
Ma'am, will you tell the process again, ma'am? After finding the domain of f of x and g of x, what should we do then?
That's the question. Now you just have after finding the domain of F and G, what should you have to do? So
Yeah.
there are two steps. So first is find the domain of F, domain of G, and the second is you have to remove. And this is for F composite G. Okay, you have to think for G composite F in the symmetric manner. Okay, so you have to remove all those X belongs to domain of G, for which G of X is not a part of domain of F.
Okay, ma'am. Thank you.
Okay, so shall we solve the question or you guys want some more time?
Yes, ma'am.
Yes, ma'am.
Okay. So here what you have to do, first we will find out what is the domain of f and g. So since the functions are very simple, so here f of x is nothing but 4 minus x squared, which is nothing but a polynomial, right? So when we know that all polynomial have domain, the set of all real numbers. So here the domain of f is nothing but all the real numbers. And what is g of x? So g of x is 1 upon under the root of x squared, right? So here is a combination of two functions, right? First is rational and the square root function. But because here we have x square, so if you put any negative values too, it will become positive. So that's why it makes sense for this under the root of function. So that's why the domain of g will become all those points where this denominator becoming 0. So it's simply x square. So when x square is equals to 0, we have x is equals to 0. So that's why the domain of g will be the all real number except the point 0. Okay, is that fine?
Ma'am, for
Now,
f of x2, when we
Mhm.
keep x equals to 2,
Mhm.
then means f of x equals to 0, right, ma'am? It becomes 0.
Yeah, it becomes 0, but 0 is a real number. No? Here, if you put x is equals to 0, we'll get 1 by 0, which is not a real number. Something we call infinity.
Okay, ma'am.
Correct?
I understand. Yeah.
Fine. Now let's try to find out what is the f composite g of x. What is the domain of this function? So here, what we have to do, we have to, this f of g of x should be well defined. So g of x should be well defined means all points from the domain of g. So that means this for all points x belongs to r minus 0, right? For which, and the second point says that we have to remove all those points for which g of x does not belongs to the domain of f. So we have to remove all those points for which g of x is not a part of domain of f. But what is domain of f? So domain of f is real number. So there is no point for which this g of x is not a point of a real number. Because ultimately, whatever input you will take, g of x will become a real number. So that's why, so this will imply there is no such x here. There is no such x. So that means we don't have to remove anything from domain of g. So here in this case, the domain of f composite g function will become simply the domain of g, which is nothing but real number minus c. Okay, is that clear? Fine.
Yes,
ma'am.
ma'am.
Okay, now let's go to the second function, which is g composite f of x. So for computing g composite f of x, we have to well define two things. First is f of x should well define. So that means x should belongs to domain of f. So what is domain of f? The set of all real numbers. And now we have to remove all those x for which this g of f of x, for which this f of x is not a part of domain of g. Right? So what is domain of g? Domain of g is real number minus 0. Right? So that means if something does not belongs to domain of g, it's simply the only one point which is equal to 0. So which will implies f of x is equals to 0. So we have to remove all those points for which this f of x is becoming 0. So when does f of x is becoming 0? So that means when does 4 minus x square becoming 0? So it simply implies that x square is equals to 4, which will imply x is equals to plus minus 2. Right? Because this is equal to plus minus under the root of 4, this is equal to plus minus 2. So that means at these 2 points, the function f of x is becoming 0. And since f of x is becoming 0, g of f of x does not make any sense. Right? G of f of x, we cannot find it to be a real number. So that's why here the domain of this particular function g composite f will become domain of f minus these 2 points, plus minus 2. That means what is domain of f? Real number minus these 2 points, plus minus 2. Okay, is that fine? Any doubt?
Ma'am, will you explain F circle Z, ma'am? Domain of F circle again.
Yeah, here. So for finding domain of f composite g, first we want g of x should be well defined. G of x should be well defined means we have to collect all those points from we have to collect all points from domain of g. So what is domain of g? So domain of g is nothing but real number minus 0. Correct? Domain of g is real number minus 0. because g is nothing but 1 by x square. So 1 by x square is not well defined when we put x is equals to 0. It will give us a infinite value, right? So that's why domain of g is real number minus z. Now here, g of x is well defined if you take any point from real number minus z. Now we have to remove all those points for which g of x is not a part of domain of f. But what is domain of f? Domain of f is nothing but whole real number. So there is no point which is not a part of real number, right? So there is no point x for which g of x is not a part of real number. So that means here in this case, we don't have to remove anything from domain of g. Because what the second step says that we have to remove point for all those, we have to remove all those x from domain of g for which g of x is not a part of domain of f. But since domain of f is a real number here, we don't have to remove any of the point. Okay, because if g of x makes sense, it means it's a real number, right?
Yeah.
So that's why
Okay,
here domain of composite function will become domain of g.
Thank you, ma'am.
Is that fine?
Yes, ma'am.
Any doubt so far? Okay, fine. Now we will discuss about exponential function. Yes, Aditya.
Ma'am, quiz 2 pattern will be same like the quiz that today the quiz 2 mock test will.
No, it's a, I mean, little bit similar to mock test. Similar means what? Mock test, I haven't seen the mock test thoroughly, but you can assume that the question pattern will be same as practice assignment and activity question. Okay.
Okay, ma'am, thank you.
Now let's go to the exponential function. Exponential functions. So exponential function means a function defined by a to the power x. Now we know that if we have function f of x is equals to a to the power x. So let's first observe the graph of this function. So suppose the value of a is between 0 to 1 and the value of is strictly greater than 1. So we have two cases here. So if the value of a is between 0 to 1, then we know that the graph of exponential function look like this. Okay, and if the value of a is strictly greater than 1, then the graph of exponential function look like this. Now using the graph, we can compute several things. Okay, one step I have to give two definitions too. So what do we understand by increasing function and decreasing function? Okay, so what is monotonically increasing? Monotonically increasing function. So this monotonic is just a word to define the nature of function. So that means you can say monotonically increasing or increasing. Both things are same. Okay, so what is a monotonically increasing function? So if you take 2 points in such a way that x1 is less than or equal to x2, and for this condition, if the function value also satisfies the same inequality, so that means if x1 is less than or equal to x2 will imply f of x1 is also less than or equal to f of x2, then such kind of function are known to be increasing function. Okay, and what are the decreasing function or monotonically decreasing function? So monotonically decreasing function. So monotonically decreasing function means if you take 2 points with the same inequality, but the value of function will make these inequality in the reverse direction. So that means if you take 2 points, x1 less than or equal to x2, then it is implying f of x1 is actually greater than or equal to f of x2. That means you are increasing the value of x. Here you are increasing the value of x, but here the value of the function value is actually decreasing, right? And here you are increasing the value of x and the function value is also increasing. So the first type of function are known to be the increasing function and the second type of function is known to be the decreasing function. Okay, is that fine? Any doubt in increasing decreasing function?
Okay, then if both the outputs are equal, then they fall in the both
It will be a
category.
constant function. Sorry, what?
In this, I mean, if both the outputs are equal, then they will fall in the both category.
Yeah. So that's why some people like to call strictly increasing function. So if you talk about strictly increasing function, the inequality will become strict. Okay, so it depends on sorry, here also it will be strict. So if they call strictly increasing, strictly decreasing, then inequality will become strict. Yeah.
Ma'am, please refer graph to.
Okay, the graph, okay. So suppose the graph are very easy for these such kind of function. So if you have, suppose you have a graph something like this. Okay, so suppose this is your graph. So suppose this is your graph, and suppose this point is suppose x is equals to 5 is the point here, right? Now from this point to x is equals to 5, let's name it to be x is equals to 1. So from this point to this point, the function showing us an increasing behavior. How you can say that it is an increasing behavior? Because here if you take any point x1, here if you take any point x2, so since x1 is lying left hand side over x2, so from this condition we can say that x1 is less than or equal to x2. Sorry, yeah, here we have strictly because it's a real line. So x1 is strictly less than x2. That's correct because it's a real line. So that's how we plot the points on real line. This is your x-axis. So now for x1, what is the output here? Output is this, right? Which is f of x2. And for x2, what is the output? Output is this, which is f of x2. So here what is happening? This x1 is also less than f of x2. So that means from the point x is equals to 1 to x is equals to 5, this function is having increasing type of behavior. Okay, so this is your increasing behavior here. Overall, we don't have, but in this interval, so what does it implies? So in the interval, close interval 1, 5, this function f is an increasing function. Now, similarly, if you observe this interval, suppose this is x is equals to 6. Now, in this interval, what is happening? If you take any 2 points, so suppose this is your x1, this is your x2, x1 dash, x2 dash. Now, here you have x1. Okay, so let's draw the same figure here. Okay, so this is your x is equals to 5. X is equals to 5 here, and this is x is equals to 6. Now, in this interval, if you take any 2 points, suppose these are two x1 and x2. So what is happening? x1 is less than x2. And what are the output? Output is this. So this is your f of x2. Right? And this is your f of x1.
Thank you,
So
ma'am.
here x1 is less than x2, but f of x1 is greater than f of x2. So that means in this interval, the function is decreasing, right? So f is decreasing in the interval, interval 5 to 6. Okay, is that fine?
Yeah, ma'am, strictly increasing is also same thing, right? From the example.
Strictly increasing, they are just removing the possibility of constant function. That's all.
Okay, okay.
So
Ma'am,
in
here
this
in
case,
the
you can say they are strictly. Yes, Roshni.
Ma'am, in the second graph, we can see that functions are also decreasing, right, ma'am? F of x1 and f of x2.
Here also it is decreasing behavior showing. So you can say it is decreasing overall. But for time being, yes, if we have interval, then how we can judge? So that's it. After
But
6
this,
also,
but between the interval, we can see that the function is decreasing, like sloping, like. So how can you decide f of x1 is greater than f of x2?
Because consider the points now. So suppose this is your input point x1, then the whatever output is there, that this will be the output point, correct? Because we have to mark the point over this line. If this is your x1, this is your x2.
Okay, ma'am. I have understood. Thank you.
Okay.
I had out here from the previous graph on the one below. So from the point of x5 here in the second graph or in the first graph, both are strictly decreasing. Whereas in the previous graph, after x is equal to 6, there is kind of turn. So there it is not strictly decreasing. Whereas in the second case, that will be still strictly decreasing, is it?
Correct. So if I make here the same type of thing, then it will be decreasing. Right?
But always the case is when you come from the left to, from my point, from my side, when I'm saying from my left, and it's going on the peak, it's always the case it will be in the strictly increasing character, right? Or even if the graph is like that, is there an opposite thing can happen, or it would be considered as strictly decreasing? Strictly increasing, sorry.
Means, see, strictly increasing means they are just removing the possibility of constant function. So yeah, whatever such kind of graph is there, they will be strictly increasing or strictly decreasing only. Only graph which is not strictly increasing or decreasing is just a constant graph. So for example, if I give you one example.
Like the steady state
one. Suppose this is graph. Okay. Now here what is happening? Up to this point it is increasing, but after this point it's behaving like a constant. So that's the thing happen if you
Yeah.
right
Thank
won't consider the strict behavior.
Yeah.
Okay. So let's get let's back to the exponential function. Okay, so exponential function we have. So suppose the a is between 0 to 1 and the a is strictly greater than 1. So we have graphs here looking like this. Okay, suppose this is going as we recorded. Okay. This is the graph of a to the power x. This is also a graph of a to the power x, but here the value of a is between 0 to 1, and here the value of a is strictly greater than 1. Before defining exponential graph, we always first fix the value of a and then talk about the function. Okay, so here we have several functions, if you can say. So if the value of a is between 0 to 1, the graph is looking like this. Now what is this y-intercept? So y-intercept is nothing, but if you put x is equals to 0, what will be the value of y? So the value of y will become e to the power 0, which is nothing but 1. So here also the y-intercept is 0 is equal to 1. And here also if you put x is equals to 0, we'll get y is equals to 1. Now here what is happening? The graph is a decreasing kind of behavior, right? It's showing a decreasing behavior. Now here the function is decreasing and here the function is increasing. Now there is one result which says that if we have a function which is either increasing or decreasing, that function is a 1-1 function. Because by the graph also we can say, so this function is decreasing function over the whole interval, right? It's sorry, over the whole domain, not a particular interval, right? So here the function is decreasing over the whole domain. So if you draw any horizontal line, it will intersect this graph at most once only. So that's why this graph, this function e to the power x is a 1-1 function for all a, right? For all a strictly greater than 0. Because if you consider this case or this case, we are observing that the graph, that any horizontal line will intersect the graph at most one. So that's why it's a 1-1 function. Is it a onto function or not? If I consider it is a function from real number to real number, then is it a onto function?
No.
No, correct. Because if you take any negative y value, then we don't have a pre-image for this value. Because this line is not intersecting our graph. So that's why e to the power x. If it is defined from real number to real number, so that means we are taking codomain to be equal to real number, then it is not a onto function.
Ma'am, this would be, I think,
No,
because
it is not a onto function for whole real number. If you restrict your codomain to be r plus, so then it will become a onto function, because then we are just we are restricting our codomain to be equal to range. Okay, so in general, a to the power x is not a onto function if we define it from real number to real number. Is that fine?
I mean, if we are restricting the codomain to be real numbers, then the range could be the set of the codomain, subset of codomain. So
If you restrict it to be the whole, not real number, if you restrict to be all positive real numbers, then. Because all real number does not have any pre-image.
the positive real numbers will be the subset of the all real numbers as the codomain and range are defined. So this should be 1-1 because for every x we have a particular y value.
It is 1 to
No,
1. The
no.
function is 1 to 1.
It is 1-1, but it is not onto. Onto means for y value, we should get an x value. So suppose you will take y is equals to -1. Then we don't have an x value which is mapping e to the power x to y is equals to -1, right?
Okay. So that's why it's not an bijective.
That's why it's not a bijective function. But what happened when we try to define the log function, what we do, we restrict this function over the positive real numbers. And then we say, since it's on 1-1 and on to both, so that's why it's a bijective function. And we define log function to be the inverse of this function. Okay, so we'll go to that. But first observe some of the properties of e to the power x. So first thing is it will be decreasing. In this case, it will be increasing in this case. Yeah, some doubts?
No, ma'am, continue.
Okay. So now let's talk about the end behavior of the function. So you guys will tell. So suppose I have in this scenario when 0 is less than a is less than 1, then limit x going to infinity, e to the power x will be equal to what will be the answers here?
Infinity and 0.
0
0
and
and here
infinity.
infinity, right? And here infinity, and then here we have 0, because that's kind of obvious, right? So as x goes to infinity, this graph is approaching toward the x-axis, that means 0 value. And as x goes to minus infinity, this graph is actually growing toward infinity. Now similarly here in this case, as x goes to plus infinity, the graph is also going to plus infinity, and as x goes to minus infinity, the graph is approaching toward axis, so that means x is equals to 0. So this is the end behavior of function a to the power x. And we already talked about range, domain and codomain. So this is the exponential function. Now with a particular value e, so we have a sequence. So if you suppose a sequence en to be equal to 1 plus 1 by n to the power n, then it turns out that this is a convergent sequence, and whatever the limit of this sequence is, so the limit of this sequence is known to be the number e. Okay, so this e number is actually very famous. It will show up in very physical scenarios. So there are some equation, some wave equation, and so many equations where we use e. So that's why this e is important. So that's why we separately study the exponential function when the value of a is equals to a. So this is known to be the natural exponential function e to the power x. Okay, f of x is equals to e to the power x. Now this function also has the same type of graph. So here the graph of function is something like this, because again the value of e is actually between 2 and 3. It's something 2.17 or 71, something like this. Okay, so that's why here the value of e is between 2 and 3. So that means it is strictly greater than 0. And that's why the function f of x is equals to e to the power x will have such kind of behavior. Okay, is there any doubt in exponential function? Anything which is not clear?
Ma'am, I've just now joined. No problem. Could you please repeat the difference between one and bijective over here?
See, bijective means 1 plus onto both things. So bijective function. So bijective functions means it should be 1 and plus onto. Right, 1 means for two distinct input we should get a distinct output, right? X1 not equals to x2 should imply f of x1 not equals to f of x2. And onto means for every element of your codomain there should exist an endpoint in your domain which maps to that codomain. So that means every point of codomain should have a preimage. Right? So that's the meaning of onto. And if you merge these two conditions, that function is known to be a bijective function. Okay, and only bijective function will possess the inverse. So if a function is bijective, then it will have a function known to be the inverse of that function, and which satisfy the composite to be equal to x. Okay, so that's the inverse definition. So suppose f is a bijective function. F is a bijective function, then there will exist another function, then there exists a function in which we denote that function to be equal to f inverse, which is the inverse of this function. So that means if f of x is equals to y, then this f inverse will take y to be its input and produce x to be its output. F of y is equals to x.
Ma'am, can we say that a power x is a 1 function because it does not have its range in negative y-axis?
No. We cannot say by that thing. Yes, it is a 1 function, but because of the horizontal line test or because of the definition of 1. If it goes to it, because see, consider this function, straight line type of function. Now it is going to negative y-axis, but still it is a 1 function and it's an onto function. So a to the power x is a 1 function, but it is not an onto function if you are considering domain to be the whole real number. Okay.
Okay, ma'am,
Is
it's
that
clear.
fine?
Yes, ma'am.
Okay, fine. So now let's go to the logarithmic function. So as I told you that how we define the log of x. So if you consider a function f of x is equals to e to the power x, And if you restrict your codomain to be all positive real numbers, so consider f is a function from real number to all positive real, right? So with this restriction, we can imply that a to the power x is 1, 1 and onto. So that means e to the power x is a bijective function. So if it is a bijective function, it should have a inverse, right? So the inverse of a to the power x is defined by log x. So we say, we define what is log of x. So we say that log base a of x is equals to y if and only if a to the power y is equals to x. Right? So that means log of a is domain. If you take x to be if you take x to be your input point, then the output will be y. And it is if and only if a to the power y is equals to x, because that's how we define f inverse function, right? So if f of y is equals to x, so then f inverse of x, so that means you will take output from here. That means f inverse of x is equals to y. So that's how we define log function. So log base a of x is equals to y if and only if a to the power y is equals to x. Okay. Now how we can judge the graph of log x. So again, here we have some restriction over a and x. So what will be the domain of log x? Can anyone judge? What will be the domain of log base a of x?
R plus.
R plus, correct? Because we know if f is a function from a to b, then its inverse will be a function from b to a, right? So that means the domain of function f, domain of f
log 0 to domain of log
yeah, sorry, R plus matlab open interval
0 to infinity or
0 to infinity.
okay.
Right? So in general, if you have a function f from a to b, which is a bijective function, so then its inverse will be a function from set b to a. So that means domain of f will become range of f inverse, and the range of f will become domain of f inverse. So same thing, since we are defining log to be the inverse function of a to the power x. So since a to the power x is a function from real number to open interval 0 to infinity, and log is its inverse, so that's why log base a of x is a function from open interval 0 to infinity to the whole real number. Okay, is that fine? Just using this fact only. Since f is a function from a to b, its inverse will be a function from b to. So now how we can calculate the graph of log x. So as we know, if we have a graph of f and we want to find the graph of f inverse, we just have to take the mirror image about the line y is equals to x. Okay, so now what are the cases here? So we have considering 0 is less than a is less than 1, and again a is strictly greater than 1. So here the graph of exponential function will look like this, right? So here if you draw a line y is equals to x, so suppose this is your y is equals to x, and you have to take the mirror image. So what will be the mirror image of this part? So mirror image of this part will become something like this. No, wait a minute. Sure. Let's go to Desmos. So mirror image of this part will look like something like this. And the mirror image of this lower red one part will look like this. So it actually goes beyond the negative x-axis.
Ma'am, could you
This
show
is
it
the
on
graph of
Desmos, ma'am?
log x. Yeah, that will be better. So here one case we have when we are taking e to the power x, right? So e is strictly greater than 1. So that means this is the second scenario. So this is the graph of e to the power x, the red one. And this is the line y is equals to x. So if you take the mirror image here, so the graph of ln of x, so ln of x means log base e of x. That's also denoted by ln of x. So this will be the graph. Now here, if we replace the value of a, since here the value of a is e, and we know that e is strictly greater than 0. So in place of E, if we replace it with 0.5, so if we replace 0.5, then this red one will be the graph, and here okay. So here the red one is a graph of 0.5 to the power x, right? And if you take the mirror image, so then the mirror image of this part, the uppermost part, will become this particular thing. The green one. This one. And the mirror image of this part, which is actually going to 0, will become this green line, which is going to plus infinity over the y-axis. So this is the graph when the value of a is between 0 to 1. Graph of log x is denoted by green one, and graph of a to the power x is this red one. Okay, is that fine?
Yes, ma'am.
So now let's try to solve one example. So this is a question for you. So find the domain of modulus of log of x square minus 2x plus 4, and answer the following question. That means first thing is it 1, 1? Second thing is it onto? Third thing is, okay, in place of a square function, let's take a simple one. Because square will become more complicated. So suppose I have a function 3x plus 4. Okay, so is it a 1, 1 function? Is it a onto function? And what else I can ask? Domain, you have to find out, obviously. Domain. Yeah, that's all. So I'll give you true or false. You can say, okay, true or false. This is also true or false. And here you will give the specific number. Okay. So I'll give you 5 minutes. So it's 9 or 12. Let's go to 9:20. Try to solve this, and also the hint is you have to use the graph. So we know how to plot the graph of such kind of functions, right? And you guys know about the scaling. Okay. And please don't use Desmos, because if you are using, I mean, in exam, you cannot use Desmos, right? So try to do it by yourself.
And does in further courses we will be allowed to code in exam?
Ma'am,
Sorry, what?
are you changing the question, ma'am?
Yeah. In place of square function, I take the linear one now, 3x plus 1. Because square, I think, will become a little bit complicated.
Yeah, I'm working with that one.
That's also fine. It won't be that complicated, but the domain will become very small. So that's why I change it to here. Small or something odd. We have to remove 2 or 3 powers.
Time over.
So it's 9:20. So shall we solve this, or you guys want some more time?
Yeah, ma'am, you can solve. I did it. Yeah.
Okay, so let's solve this. I have some of the answers. So let's first solve the domain part, because see, it's a composite function if you realize. So if you take one function to be your modulus of x, so suppose if you take f of x to be equal to modulus of x, and if you take g of x to be equal to log of 3x plus 4, then this function, let's name it to be h of x. So this h of x is nothing but f composite g of x, right? Because what is f composite g of x? It is actually f of g of x. So what is g of x? So this means f of log of 3x plus 4, and f is a modulus function, which is modulus of log of 3x plus 4. So it is a composite function. So we know how to deal with domain of composite function. So here you observe that f of x is equals to modulus of x, and we know that modulus of x is well defined for all real numbers. So that's why domain of f will become the all real number. Now what is g of x? G of x is log of 3x plus 4. Right? So we know that log function is well defined only for values x between 0 to infinity. Right? So g of x is log of 3x plus 4. But we know that log is well defined. Log is well defined for only for right? Log is well defined only for values 0 to infinity. So that means this is also, this g of x also you can think about a composition of two functions. One is the linear one and the second one is the log of x. So that means again we can take g of x is a composition of two functions g1 and g2, g1, g2 of x. Where this g2 of x is your 3x plus 4, and your g1 of x is nothing but the log function, log of x. Right? So it is a composition of three functions you can imagine. H of x is a composition of three type of function. Now we have to find out domain of G2 if you want to find out the domain of F composite G. So what will be domain of G? So domain of G means where this log of 3x plus 4 is well defined. But when log is well defined only for the values between 0 to infinity. So we want to find out all those values which for which this 3 of x plus 4 is not a part of 0 to infinity, right? So that means, so since we know, but also you can find out domain of G using these two composite function also. But let's won't complicate it. Just go by the fact that log is well defined for all those values between 0 to infinity. That means for all those x for which x is strictly greater than 0. So what we want? So we want this quantity 3x plus 4 to be strictly greater than 0. But when we have 3x plus 4 strictly greater than 0, when 3x is strictly greater than minus 1. That means x is strictly greater than minus 4 by 3. Okay, so if x is strictly greater than minus 4 by 3, so what does it mean? So it means if the value of x is strictly greater than minus 4 by 3, it will implies this 3x plus 4 is strictly greater than 0, and it will implies log of 3x plus 4 is well defined. Right? So that means log of 3x plus 4 is well defined for all those x for which 3x plus 4 is strictly greater than 0, and 3x plus 4 is strictly greater than 0 means x is strictly greater than minus 4 by 3. So what does it imply? So it implies x belongs to minus 4 by 3 to infinity. Correct? So this will be the domain of gx function, which is actually equal to log of 3x plus 4. Is that fine? Any doubt in domain of log of 3x plus 4? So I think you guys answer minus 3 by 4, but yeah, 4 by 3 is correct. So that's also fine.
Ma'am, range would be from 0 to infinity, right? Like
range will
we
be
take
0 to
mod.
infinity because it is a modulus function. So that's why it is not an onto function. Right. So let's find out that, but still we haven't got the domain of the whole function. The whole function is modulus of that. But since here f of x is modulus of x, so again, the domain of f is the whole real number. So that's why we don't have to remove anything else, right? So because what will be the next step? So the next step will be we have to remove all those x from domain of G for which g of x is not a part of domain of f. But again, domain of f is real number, so that's why we don't have to remove anything. So ultimately, at the end, what will become? So the domain of this function, modulus of log of 3x plus 4, is same as domain of G, which is nothing but minus 4 by 3 to infinity. Okay, so this is your domain, minus 4 by 3 to infinity. Is that clear? Fine.
Yes, ma'am. Please.
Okay. Now
Hello,
let's.
ma'am. Can you explain this statement which you have written? Next step, remove x belong to DG for which?
Yeah, so in composite function, we follow two steps, right? First, find the domain of G, find the domain of F, and this will be our second step. So second step says, if you want to find out the domain of F composite G, that means you want this expression to be well defined, f of g of x. So you have to remove all those x from domain of G for which this g of x is not a part of domain of f. Because if g of x does not belong to domain of f, the f function cannot act on this particular quantity g of x. F of g of x does not make sense. So that's why. But
Okay,
here,
okay, ma'am.
fine.
Yeah,
But here
yeah.
it's a real number, so we don't have to remove anything. So that's how we compute it. So domain is become minus 4 by 3 to infinity. Now ontoness we can simply judge, because since it's a modulus function, it won't take any negative value. So that's why it's not an onto function. So here we have false. So no, I mean, why don't you guys judge about ontoness? I mean, I have just only one answer. So see, whenever you see the modulus function, just hit that it won't be on, because it's a modulus function. It will always take positive values. So for all those values which are negative, we don't have a pre-image. So obviously it's not an onto function. Okay, so this will implies f is not an onto function.
Ma'am, you're telling indirectly for negative y-axis there is no pre-image.
Right, because it's a modulus value, right? Mod function is
Yes,
there.
ma'am. Only for positive, like it's positive only. The range is only positive. You mean to
Yeah,
say?
range will
What
be
if
only
the
positive.
codomain is restricted to positive
But no,
or
here the codomain is, see, whenever a codomain is not given to you, just assume to be whole real number.
Ma'am,
That's a
then
usual
even if it's
convention.
not the modulus function, then also it won't be onto na, because our domain is restricted to minus 4 by 3.
No. It will be onto, because see, log function is onto. Still domain of log is 0 to infinity. Right? Log function's range is what? The whole real number. So that's why it's a onto function. So see, log of, if you compute the graph of this function, so let's try to do that. Now we have to judge one-oneness, but that one you can do via two methods. So first thing is, you can use that, since we have a log function, we can actually find two values for which one negative value, one positive value, for which the output will be same. This will be the one method. And another one is, you can judge by the graph. So let's go via the graph. So we have to first draw what will be the graph of log of 3x plus 4. Right? But here this 4 is just a constant. So this graph will be similar to log of 3x. Okay, only just shifted by a scalar 4. So it will shift it. I mean, if we have a graph of 3x, then the graph of 3x plus 4 will be 4 unit toward the left hand side over the x-axis. So we'll see this by Desmos. So let's try to draw the graph of log of 3x. So log of 3x means, so here, since base is not given to you, so whenever there is no base mentioned, we suppose that it's a base 10. That means the value of a is 10. So strictly greater than 0. So log of 3x is also look like something like this, right? As usual, our log functions graph. Little bit stretch, you can see. But here we have to draw.
So let's try to draw the graph of log.
So now this is the graph of log of 3x. Now what will be the graph of log of modulus of log of 3x? So we know that whenever we want to find out the modulus graph, we just take these all negative values and turn them toward the positive values. So that means the modulus graph will become something like this. So here up to we have the same values, because over this over these values, over the positive y values, modulus function act like an identity, right? It will give us as it is. But for this negative value, it will reflect it over here and go something like this. Or more precisely, if you want, then it will be something like this. Will happen. Okay. So this is, it won't actually cross the
Ma'am, could you draw it
y-axis.
on Desmos, ma'am?
Yeah, I'll draw that.
Ma'am, it will be parallel to somewhat y-axis, right?
It will be parallel to somewhat y-axis because it's a log of 3x. Now, what will be the log of 3x plus 4? This graph will only shift toward the positive, shift to 4 unit toward the left. Okay. So, but what is the main purpose here? You have to observe this behavior. Now, here, if you draw a horizontal line, that horizontal line will intersect 2 points. So, that's why from here we can say it is not a 1-1 function. Is that clear?
Hello, ma'am. I have the question that if we remove the modulus function, then how it would be onto?
Yeah, I'll show you how it would be onto. Let's go to the Desmos. Okay, so this is the graph of log of 3x plus 4. Now here, suppose I will remove the modulus function. Now see what will be the graph. So this will be the graph of log of 3x plus 4. So instead of 3x plus 4, let's consider 3x. Now here you observe that over the minus infinity, I mean over as x goes to 0, the graph will approach toward minus infinity. So that means all negative values will have pre-image. But here plus infinity also, as x goes to plus infinity, we know that log x was also going to plus infinity. That means as you increase the value of x, this graph also grows to plus infinity with very small rate of change. So that means here the increase is very small, but still it is increasing. So observe the value. So here it is increasing, but it is increasing very slowly, but it is increasing kind of behavior. So that means as x goes to infinity, log of x is also going to infinity. So that's why here the range is real number. So whenever we have real number range, so that means onto function. Is that fine for you, Laksh?
Ma'am.
Yes, ma'am. Yes, ma'am.
Ma'am, can we have a modulus function for this
Yeah.
log 3x?
So suppose I'll take modulus here. So this is the modulus function. So it will look like something like this, parallel to y-axis. Because what does it, what does mod do? So suppose this is another function. So the original function is this function, the yellow line behind this. So as we take the mod, this whole negative part shifted toward the positive thing, right? In the same way. So that means the nature is same. Something like you can say if you put a mirror here, mirror over the x-axis, you will get that this violet line is nothing but the mirror image of this particular red line. Okay, so that's
Ma'am, at x equal to 1, will there be a sharp edge? For,
there will be sharp edge. That's why it won't be differentiable.
Sorry, 1 by 3. X equal to 1 by 3.
1 by 3 in this case. Now what happened? If we add 4, it just gets shifted 4 unit toward the left hand side. Okay, so the nature of graph will be same as 3 of x. So that means it won't be a 1-1 function.
So, ma'am, can we generalize like any log function with a constant that is mod? It is not a 1-1 function because the horizontal test will fail. Can we generalize to any log with the
you can generalize to any log. But the thing is, you have here a linear function, right? A linear kind of function should be there. Then you can generalize it.
Okay. So if it is a quadratic function, then it won't.
Actually, quadratic function, there are some problems. So what happened? So suppose I'll take quadratic here. So it will have a very random kind of behavior. So
okay.
You are seeing the blue line, right?
Yes.
So that's why it is a little complicated. It's not that tough, but yeah, it will have a little complicated. Fine. Any doubt? Okay, Divya, you have any doubt? Okay. Fine. So that's the one thing I want to tell. Now another way of predicting that. So range you can easily see by the graph also, but range is 0 to infinity, correct? Because since it's a modulus function, it will take all negative value. It will convert all negative y values into positive. So the range will be 0 to infinity. Okay, so that's why it's not a onto function, because if codomain is not given to us, we generally assume that codomain is the whole real number. Okay, fine.
Hello, ma'am.
Okay.
Yes, Shweta.
Ma'am, could you please explain something about this asymptote, horizontal and vertical asymptote?
Okay. So see, asymptotes are what? So we are familiar with the tangents. Okay. So what are the tangents? So for any graph, a tangent is nothing but a line which touches the graph exactly at one point. So this line is known to be a tangent. So what is an asymptote? Asymptote is a line which kind of seems to be approaching toward the graph, but it never intersect the graph. So for example, if you consider log x, so suppose I have this graph of log x. So suppose this is something like this. So then here what is happening? This graph seems to, or this line y-axis, okay, so this y-axis seems to intersect with the graph at infinity, but it never actually intersect. So which is what we can say, some kind of approaching toward graph behavior is there. So that's why this line is known to be the asymptote of log x. So a line which seems to be approaching toward the graph or seems to be intersecting with the graph at infinity.
Hello, ma'am. Yeah, I got that. But what happened when there is no x-axis point or not x-axis or y-axis different than values of 0?
Different than x.
Yeah.
So then you can consider any horizontal line. So suppose we have this kind of behavior, right? So here if you draw any horizontal line or any vertical line, no matter horizontal, vertical, or any line, so you have to find out asymptote is nothing but a line, as like tangent. So what are the tangents? Tangents are also line. So here, okay, so suppose I'll tilt this graph a little bit. So suppose you have this kind of graph, right? So here, if you draw a line, something like this, okay, which seems to be intersecting the graph at infinity, then this line is also known to be an asymptote. It is not the case that you should have always y-axis or x-axis or any horizontal or vertical line. You can take any line which is showing such kind of behavior. Then it will be an asymptote. Fine.
Yeah, ma'am. But you know how to find, because I think in week 5 in some functions e raised to something plus something, in that there we have to find the asymptote.
Okay, fine,
I don't know how to
So
find
see,
that.
whenever you want to find an asymptote, so what is asymptote? So asymptote is a line which seems which shows such kind of behavior. So ultimately what you have to do, so in this case, in such cases, it's actually very difficult to find the asymptote when it's not a y-axis or x-axis or any horizontal or vertical. But if you have a graph which actually possesses the horizontal or vertical line, then that equation of line or the value of line is nothing but the limit of function. So for example, I have this kind of graph. Okay, so for this graph, what is happening? So here this line is the asymptote, right? So suppose this is y is equals to -10, right? So y is equals to -10 is the asymptote. So that means as the graph is growing toward this direction, this line seems to be intersecting with it, right? So ultimately what is happening here? So here you observe that if you find the limit of this function f of x as x goes to infinity, the limit is nothing but the value of asymptote here, which is nothing but -10. So that's why if we have horizontal asymptote, then we can actually find it via the limit. So I think in our course we only talk about the horizontal asymptotes. So if someone asks you about the asymptotes, you have to find out limit x going to infinity of f of x and limit x going to minus infinity of f of x, because it could happen that the function can have two asymptotes, two horizontal asymptotes. So for example, I have this kind of behavior, this function, right? So then this function, so suppose this is y is equals to -10, y is equals to 8, -8, right? So then here we have y is equals to -8 line as an -8 line as in my asymptote, and here we have y is equals to -10 line as an asymptote. So whenever someone asks you to find out the asymptote, you just have to find out these two limits, and whatever value will be there, those two lines will be our asymptote.
I got
Is
it,
that
ma'am.
fine?
Thank you. Yes, ma'am. Yes.
Okay. So in general, the asymptote could be anything, but that will be little. Yes, Lokesh.
Is it possible to have a asymptote for every graph now? Which is
No,
sine
actually,
graph
it's
or
not the case. For example, if you consider the polynomial, So polynomial does not have any asymptote, because polynomial will have here the value of limit could be infinity or minus infinity kind of thing, right? So it is not the case that every
Yeah.
graph possesses the asymptote.
Yeah. Okay.
Yeah. Okay. So in such scenario, actually asymptote can be found, but it has a very precise formula as we have for tangent. So here also we have some formula for finding out the asymptote, but let's not worry about that. We just have either horizontal asymptote or at max vertical. Okay, so yeah. So this is for horizontal asymptote only. Horizontal. If you want to find out the vertical asymptote, then you have to consider the other way around. So other way around means you have to find out as y goes to infinity. So then you have to find out for those values of x. Okay, so I will make this as a remark. So remark is, so first is for horizontal asymptote. So for a horizontal asymptote means something line y is equals to b. So for this thing, you have to find out these two limits. At limit x going to infinity f of x and limit x going to minus infinity of x, minus infinity and limit x going to infinity f of x. But what happened? Horizontal asymptote means such kind of asymptote. Right? But what happened if you have a vertical asymptote? For vertical asymptote. So for vertical asymptote, you have to consider those values of x for which the function is growing to infinity. So that means you have to find those a comma b for which if you consider limit x going to a, f of x is equals to either infinity or limit x going to b, f of x is equals to minus infinity. Right? So vertical, for a vertical asymptote, you have to find out such value of a and b. Then this line y, then this line x is equals to a and x is equals to b will become your asymptotes. And here, the whatever the limit will be, so suppose this limit is a, this limit is b, then here y is equals to a, and y
minus
is equals to
infinity,
b.
not b.
Oh, sorry. I told minus x. Thank you. So here the line y is equals to a, y is equals to b will become asymptote, and here this will become. So for this scenario, we have a very particular example, which is log x, right? So we know that the graph of log of x when the value of a is between 0 to 1, something look like this, right? So here you observe that this y-axis is working as an asymptote, because what happened if you compute the limit x going to 0, right? Limit x going to 0, I have because vertical line will have equation. Correct. So here, if you compute limit x going to 0 log of x, then this limit is nothing but plus infinity, right? So that's why here x is equals to 0 is the asymptote, a vertical asymptote. Okay. So these are the two cases for a horizontal asymptote and for vertical asymptote. Overall, in our course, we just talk about asymptote of either e to the power x or log x. So whenever we have log x, there will be vertical asymptote. And whenever you have e to the power x, there will be horizontal asymptote. So horizontal asymptote is we can find easily just by computing the limit. But for vertical asymptote, we have to guess some quantity where such kind of limit may exist. So in case of log, it's usually when x goes to 0 or whatever expression is given in between the logs. So for example, 3x plus 4 or x square or something, whatever given in the bracket of log, that goes to 0. Okay. Is that fine? Okay, so now let's do one example, quick example. So example is what will be the asymptote for modulus of log of 3x plus 1? Can you guys guess?
Yes, ma'am, it's minus 4/3.
Right. So the line x is equals to minus 4/3 will be the asymptote, because as x goes to, if you consider this limit x going to minus 4/3 of modulus of log of 3x plus 4, it simply says that as x goes to minus 3/4 means limit 3x plus 4 going to 0, modulus of log of 3x plus 4. And we know that as x goes to 0, this limit goes to infinity. So that's where this will be your asymptotic. Is that fine?
Yes, ma'am. I able to calculate this using graph, but using equation, it seems difficult for me.
Right. I hope this is clear now. If you guys have any doubt, you can ask. Because that's all from my side. One thing I have left is the properties of log, because here we just have formulas. So if you guys want to go through them also, I can do it. Or else it is fine. I mean, there are 5 to 6 property. Let's quickly recall what are the properties of logarithmic functions. So first thing is
Ma'am, one strange thing that I noticed in the practice assignment, there were in the log section, there was something which was having multiple bases and multiple inputs in one expression.
So there what you have to do, you have to use the property of log to generalize the base. So there is one property of log now which says what is this? This property, that log base a of some value c is actually equal to, you can actually convert the base into one thing. So suppose this is c and log base b of c. So here there is one single base, and you can convert the base a into base b using this formula. So you have to apply this property there. To first uniformly convert the bases, and then you guys are familiar with converting into polynomial method, right? So whenever you have something left hand side is equals to right hand side, so what you have to do, you have to make some substitution which will convert your expression into polynomial. So for example, I have this expression. Suppose this is log x 3 by 2 plus log of 2 by 3 of x is equals to 1. Suppose I have this one random equation. So here what is happening? This base and this base are different. So it's very tough to handle such kind of logs with different bases. So what we do, we use this property and change it into 2 by 3. So for that, we have to apply. So that means log base 2 by 3 of x is actually equal to log base 3 by 2 of x and upon log base 3 by 2 of 2 by 3. Right? But this is same as log base 3 by 2 of x. And this is 2 by 3. We can write it in terms of inverse. So that means this is 3 by 2 to the power minus 1. Correct? So what you can do, you can pull this minus 1 over the here, and we'll get minus of log of 3 by 2 of x and upon log of 3 by 2 of into 3 by 2. So which will become 1. So it is minus of log of 3 by 2 of x. So ultimately this, so suppose this actually doesn't make sense. So suppose I have something like 2 and then the whole square of this. Okay. Suppose this is equal to. So now what we can do, we can just substitute our whatever calculation we have done. So it will become log of 3 by 2 of x and plus 2 times of minus of log of 3 by 2 of x, the whole square is equals to 1. Ultimately, our goal is to find the all values of x which satisfy this particular equation. So here what you do, you will substitute in place of log of 3 by 2 of x something like t. Okay, and then convert this whole expression into a polynomial, because we know that polynomials are very easy to handle as compared to log and exponential. Okay, so it will become t plus 2 of minus of t square is equals to 1. So that means so this is square. So it will become 2t square plus t minus 1 is equals to 0. Right. So now we know how to handle this polynomial, find out the root and do the calculation. So this is one very famous method used for solving such kind of problem. Whenever you have such kind of problem, try to convert it into equal bases and try to substitute something which will change your expression into polynomial. Okay, is that fine? I think sir also did one example using this particular method. Yeah,
Yes, ma'am. Yes, ma'am.
Hello, ma'am. Can you please explain the part where you have changed the base of the logarithm?
Yeah, sure. So here what we do, we uses this particular definition that log base a of x is actually equal to log base b of x and then log base b of a. Okay. So I want to convert this 2 by 3 into 3 by 2. So that means this log base 2 by 3 of x is actually equal to log base 3 by 2 of x and upon log base 3 by 2 of 2 by 3. But what we can do, we can say that this 2 by 3 is actually equal to 1 upon 3 by 2, right? And this is same as 3 by 2 to the power minus. So that's how we can change 2 by 3 to 3 by 2. So
Okay,
this will
ma'am, got it.
implies, got it?
Yes, ma'am.
For 5th and 6th week, we have done the revision.
I have doubt in week 6 graded assignment question number 7.
Hello, ma'am. Session is over or what?
Yeah, so from my side, it's over. If you guys have any doubt, then you can stay. We can discuss those.
Hello.
Yeah. And can you please check out the message section? I've just sent the screenshot of the thing that I saw. That was
I haven't gotten any screenshot.
I've
Are you
just
sure
put.
you have messaged me? Because I have turned it into everyone, so maybe it got to someone else. Please send
Okay.
it back.
Okay.
Okay, so what's your doubt here? You have to solve this expression. Someone asked the question number 7, right?
Yes, ma'am.
So choose the correct answer. The jeweler sold 540 kilogram gold in 2019. So here they say that amount of gold sold by a jeweler on the mth day of 2019 is given by the function. So okay, so mth day is given by this function. So what will be the last day of a year? So last day of a year is 365, right? See, 363 or whatever the quantity is there. You have to multiply that with your value here. So this will give us, yeah, so here it's given that where m is equals to 1 corresponds to 1st January 2019 and m is equals to 365 corresponds to 31st December of 2019. So if you want to find out the jeweler sold how many kgs of gold in 2019, just substitute m is equals to 365 and compute the value. That will give you the answer. Are you getting my point, Priyanshi?
Yes, ma'am. Ma'am,
just substitute m is equals to 360. Yes.
Ma'am, in question number 10th, how do we know that our graph is the having the root of log x option? How option number 1, 2, 3, fifth option is correct?
How option number 5? Okay, so the graph of f of x could be a graph of log. Okay, so this option is actually a little bit tricky to handle, but see here what is our log function. So log of some polynomial is given. Now what is this polynomial? So what is the degree of polynomial? So degree of polynomial will be, okay, so let me paste this question here. This is your question, right? So here for option number 5, so see option number 5, what this is say that the graph of f of x could be a graph of log of this function. Now this is a polynomial. So what is the degree of this polynomial? So there are 1, 2, 3, 4, 5, 6, right? So degree of this polynomial is nothing but 6. So that means it's an even degree polynomial. Okay, so what you have to do here, you have to observe something. So so the first thing is we know that as x goes to 0, the log of x function will goes to plus infinity, correct? So as x goes to 0, log of x goes to minus infinity, if since our base is 10 here. So right, because this is the graph of log. So as x goes to 0, the graph of log goes to minus infinity. So now here you observe that this is our polynomial of degree 6, right? So now that means, so this polynomial could have 6 roots. So here you observe that if you substitute these values, so suppose if you substitute x is equals to minus 2, then this factor will become, but log 1 is equals to 0, right? Yeah, so if you substitute x is equals to minus 2, this factor will become 0 and we'll get log 1, which is also equal to 0. So that means graph intersected this point. So that's a correct information. Here also, if you, what I am saying, so if you put x is equals to minus 2, this whole function log base 10 of whatever this will become 0, right? So that means this point is correct. Similarly, if you put x is equals to 3, what you will get? We'll get this bracket to be equal to 0. So that means ultimately we'll get log base 10 of 1 plus 0, which is again log base 10 of 1. And we know that log of 1 is nothing but 0. So that's why this point is also correct, and similarly this point is also correct. So that means these are the point where our graph is intersecting the x-axis, and those values are correct. Similarly, here 5 is there, so this is also correct. Now what you have to judge? You have to judge one thing using this particular behavior. So what does it say? So as x goes to 0, this log base 10 of x goes to minus infinity. So now we have to judge where this x goes to 0 can happen. Okay. So now this is a 6-degree polynomial. So there could be terms where this kind of behavior happen. I mean, if this is a 6-degree polynomial, then there will be at most 5 turning points, or you can say 6 root can happen. So that means there will be 6 nature where 6 points where such kind of scenario can happen, right? So since this p of x is, which is this 1 plus the whole brackets are there, and it's an even degree polynomial. Even degree, actually this degree does not give us anything, but yeah, so since the degree is 6, so there are at most 6 roots. So that means there are 6 points where this x goes to where this px goes to 0 can happen. So here you observe that since we know that as x goes to 0, this log of x goes to minus infinity, right? So that means as p of x goes to 0, this log of x will also log of p of x will also goes to minus infinity. So that means there will be 6 roots where such kind of minus infinity behavior is happening. So there is a 1, this is also 1, this is also 1.
Ma'am, how
So there
minus
are
infinity?
exactly 6. Sorry, what?
Ma'am, when x goes to 0, it goes to infinity, na? How minus infinity?
No. As x goes to 0, log will go to minus infinity, no? Because the graph of log is this. So as you approach 0, the graph will go to minus infinity.
Yes, ma'am, yes.
Huh. So here there is one thing is this minus infinity behavior is happening up on zeros of these functions. But here this plus 1 is there. So yeah, but if log of this p of x goes to minus infinity, no, then log of 1 plus p of x also goes to minus infinity. So this thing we can actually say. Okay, so let's recall what are the points I want to say. So this is our graph. So here we know 2 points. So one thing is that these all points, whatever x-intercept is given to us, those all are correct. Okay, just by observing the point. Now here we use the fact that as x goes to infinity, as x goes to 0, the log base of x, the log base 10 of x, this actually goes to minus infinity. Okay, this fact is known to us. Now what we can do, so since we know that if you consider a polynomial p of x to be equal to this polynomial, x plus 2, x plus 1, x minus 3, up to x minus 6, whatever this is, then there are 6 roots are there, right? So if you put x is equals to minus 2, then also px goes to 0. If you put x is equals to minus 1, then also px goes to 0. So that means this px is actually, this p of x is actually going to 0, as x is going to minus 2, as x is going to minus 1, x is going to 3, x is going to 4, 5, and 6. Okay, 4, 5, and 6. Okay, so whenever x approaches to minus 2, this px approaches to 0. As x approaches to minus 1, this px approaches to 0. But as px approaches to 0, we know that log of p of x, this will approach to minus infinity, right? Because of the same fact, as x goes to 0, log of x goes to minus infinity. So here in place of x, we have p of x. So as p of x goes to 0, this log of p of x goes to minus infinity. But here this one constant is there, but that's also a true thing. So if log of px goes to minus infinity, then log of 1 plus px also goes to minus infinity. As we saw the same nature for log of 3x and log of 3x plus 4, correct? Log of 3x graph will be something like similar of log of 3x plus 4. So that's how we can say that this behavior is actually true. But there is a little mistake here that I cannot say mistake, or overall it's actually true. So with this method, we can actually say that it could happen that this is a graph of log base 10 of 1 minus the whole polynomial, 1 plus the whole. Okay. Is that clear for you, Priyanshi? Any
Yes,
doubt?
ma'am.
Yeah.
Ma'am, there is one more doubt. In week 7, graded assignment question number 10th.
Okay, so I will discuss this Rajiv question. Copy it. Then we'll go to that question. Okay, so what's your doubt here, Rajiv? Hello? Okay, so here this fractional part is there. So fractional part means this is defined like this, right? So fractional part of 1.32 is actually 0.3. So here what we have to know that is the statement true or false, the left hand limit and the right hand limit of the given function fx exists at x is equals to 0. Okay, so here and this is the greatest integer of floor function. So f of x, if you consider, so here we have a floor function, so which is a x plus 1 floor function when minus 3 is less than equal to x is less than 0. So what you have to do, you have to consider the floor function near to 0, right? So that means if you take, you have to change this expression near to 0. So here, if you change this to be near to 0, so that means if you consider x to be very near to 0, then what will happen to the floor of x plus 1? So the floor of x plus 1 means the greatest integer less than or equal to 0. So if you consider any point, yeah, so if you consider any point from minus 1 to 0, right? So if you consider x from minus 1 to 0, x plus 1 will be from 0 to 1. Right? So if you take x from here, this is your x plus 1. And the floor of x plus 1 will take the greatest positive integer less than or equal to this quantity, which is nothing but 0 itself. So that's why if you consider the expression very close to 0, then it will become 0. Right? When x is equals to 0 is there, it is although 0. And when you have this fractional part, right? Fractional part of x plus 1. So if you take any point in the interval 0 to 1, so suppose we have a point from, if you take any x which is between 0 to 1, this is 0 and this is 1. So if you take any x here, so for this x, where does x plus 1 lies? So x plus 1 lies over here. That is 1 to 2. But yeah, see, fractional part of 0, this is also goes to 0 as x goes to 0, right? Because this plus 1 actually won't change. So yeah, so one thing I have missed here is the fractional part of x plus 1 is same as fractional part of x. You can use this fact to show that fractional part of x goes to 0, right? So actually what happened, this fractional part function remove all the integer parts. So this fractional part of x plus 1 is actually same as fractional part of x, no matter whatever x you will choose. And we know that this goes to 0 as x goes to 0, because this is nothing but x only. If we come around 0 to 1, right? If you take any x here, the fractional part of that x is same as x. So that's the one reason that it also goes to 0. So that's why its option is true. That because left hand limit will be 0 because it is behaving like a constant near to 0.
Yeah,
And this is also 0 and this is behaving like an x when you take very small neighborhood of 0.
Ma'am, sorry, ma'am, for the left hand part alone, ma'am, can you please explain that again, ma'am? Because I just applied x equal to 0. I got one answer, ma'am. But you're saying that it should be 0. So just want to understand.
Right. So see, understand what is this fractional part. Okay, so fractional part function actually give us the it will leave out the integer part, right? So that means fractional part of 1.356. This is nothing but 0.356.
Yes.
Okay, so here you observe that no matter you will take whatever integer you will take, you will always get whatever thing is here 0. Right. So that means the fractional part of 1.356 is also 0.356, and the fractional part of 2.0356 will also equal to 0.356, because we have to consider the terms which are after the right. So that's why this fractional part of x plus 1 is same as fractional part of x. And this goes to 0 as x goes to 0. Okay.
This is fine, ma'am. The first one, the left hand side limit, ma'am, which has like.
Okay. So see, left hand side limit, what you have to consider, we have to consider floor of x plus 1. Okay. Floor of x plus 1 means greatest integer less than or equal to this function. So suppose you have any point over the number line. So suppose you have integer here. So suppose this is some integer n and this is some integer n. And if your x lies between n and m, so what will be the floor of x? So floor of x will be the next, will be the closest integer which is lying toward the left hand side.
Correct.
Because this is the greatest one which is less than or equal to. So here what we have to observe, we have to find out the value of floor near x is equals to 0. Correct. So that means when x belongs to open interval -1 to 0. Right. So if x belongs to open interval -1 to 0, you can imply x plus 1 belongs to open interval 0 to 1. Right. Because just a jump. Right. So if x is here, so which will imply this x plus 1 will be a part of this interval 0 to 1. Right. So if x plus 1 belong to 0 to 1, what is the greatest integer less than or equal to this quantity? The leftmost one. So the leftmost one is 0. So that's why this floor of x plus 1 will behave like 0 near, or you can say over the left hand side of 0. Okay. Is equal to 0 for left hand side.
Okay, ma'am. So again, as you did for the fraction part, ma'am, here also I can say that the floor of x plus 1, I can simply take it as x only, right, ma'am? So which is
not
again
x
0.
actually. Typically 0, exact 0. Because the floor function will give us only integer value, whereas x function, I mean the fractional part function give us the whole value. I mean the values will change, so it will be 3 point something. Because if you consider the graph of fractional part function, so the graph looked like something like this. This is the graph of fractional part function. Okay, and the floor, if you draw the function, if you draw the graph of this particular function, you'll see this kind of behavior over there. So suppose this is -1. So up to -1 to 0, this is the value of floor of x plus 1, and this is the value of fractional part of x plus 1. So that's why here from the graph, it's very easy to say that it's a continuous function.
Okay.
Fine. Yes, Priyanshi, this is your doubt?
Yes, ma'am.
This one, consider two function f of x and g of x.
Yes, ma'am.
So what's your doubt? We have h of x, you can easily find out. It's nothing, just an expression. You have to compute the domain, right?
How can we solve the option number second?
Second option, okay. So what the second option says, h of x, what is h of x? F composite g of x, okay. So h of x is actually equal to f composite g of x. So that means first I have to apply g on x. What is g? So g is under the root of, so it is under the root of 2x. And now you have to apply f on it. So f in place of x, wherever you see x, just put under the root of 2x. So it will become under the root of 2x to the power 4 log of under the root of 2x into under the root of 2x. So yeah, this option is correct.
In the next question, it is asking when the hx will take the value 64. How can we solve this?
And okay, so it says that when hx takes the value 64, na?
Yeah, hx value is equal to 64.
Okay. So suppose we take hx to be equal to 64. So this is the expression for x. So under the root of 2x, 4 times log of under the root of 2x under the root of 2x is equals to 60. We have to find the value of x, right? Find x. So what we can do for simplify such kind of expression, we'll just take t is equals to under the root of 2x.
It is not 6, it is 64.
Yeah, sorry, 64. Yeah, right. So if you take t, it will become t to the power 4 of log base t to the power t, right? But we know that log base t to the power t will become 1 because log base a equal to 1. So it is equal to 64. So it means we just want to compute t to the power 64, t to the power 4 is equals to 64. So that means, which will imply t to the power 4, that means t to the power 4 minus 64 is equals to 0. So if you apply, if you solve this, it will become t square minus, the 64 is what? So 64 is, what is the fourth root of 64? 2 is not there. So 64 means 2 to the power 5. So that is 2 root 2, you can say. Right. So, but in place of 2 root 2, we have here 2 root 2 square and t square plus 2 root 2 square.
2 power 5 will become 32.
Yeah, 2 to the power, 2 to the power 6 will be there, no? So 2 to the power 6, still it will be, yeah, so 2 root 2 is only there, no? 2 root 2, 4 root 2.
Hello,
Yeah,
ma'am.
fourth root of 2 will be there.
Hello, ma'am. Just replace t
Yes.
raised to 4 with root 2x.
Okay, that will help.
Yeah.
Yeah, then it will become square, right? So here it will get to under the root of 2x to the power 4 to the power 64. So this is same as 2x square is equals to 64. Now it's easy, right? So that means 2x can be equal to plus or minus 4, plus or minus 8. Sorry. So which will imply x is equals to plus or minus 4. So this is your answer. X is equals to plus or minus 4. But we cannot take minus 4, I guess, because here g of x is under the root of 2x. So the answer will be, I mean, we cannot take x is equals to minus 4 because since g of x is equals to under the root of 2x, so g of minus 4 is not well defined, It will give us a negative quantity, right? And what is our h of x? H of x is actually f composite g of x. So if g of x is not well defined, we cannot say f composite g of x is well defined. So that's why the final answer will be x is equals to 4. Is that fine? I have done correct calculation, I guess.
Yes, ma'am.
Okay, fine.
Week 7 graded assignment question 10.
Hello, ma'am. Before that, could you please tell how to find domain in the same equation, the previous question, because there are two options in which they are asking for the domain.
Okay, so this is domain of function f of x is the interval. So you want to compute the domain of f of x and domain of g of x, right?
Yes, ma'am. But how to do that? It is getting
So
tricky when log and exponential function comes. Somehow I don't know what happened with me. I get nervous.
Right, excellent. So see, f of x is what? X to the power 4 times log of x to the power 2x here, right? So here there are so many x. So what we can do, we can actually think about it. What we want to find out, we want to find out all those values of x for which this quantity should be well defined, right? So the first thing is this is exponential x to the power x kind of scenarios there, right? So the only restriction we have to say is over here, because this is exponential function, it will be defined for all things, right? So the only thing which is undefined here is log base x and this x. So we know that if we have a for which we want to define log base a of x, so what are the condition over a? So we say that a is strictly greater than 0 and a is not equals to 1. Okay, so this is a condition for a. So that means one condition I have for x, that x should be strictly greater than 0 and x should not be equal to 1. Okay, so this is a one condition. And for log x also, so what is for this x also? What are the conditions we have? That this x should be greater than 0, right? So that means x should be strictly greater than 0. So that means overall the domain will become, so this will implies f of x will become this is log base a x of x is there, no? So it will equal to 1 for all x. Isn't that the case? Because we know log base a of a is equals to 1.
I guess it's simply 4 x
X
raised
to
to
the
4.
power 4 then.
Yeah.
Then the domain will become the whole real number.
Real number.
We don't have to consider anything. Right.
So we have to,
this option should not be correct.
okay.
Ish. Okay. And I think they just have given to confuse us. Log x to the power x, because log base a is 1, so this will become 1 for all value of x, no matter whatever we'll take. So ultimately f of x is just x to the power, which is a polynomial, so the domain will be whole real number.
And ma'am, the last option, the domain of the function 1 upon root 2. What is that? Root
So
g of
here
x.
you can use composite function. So you can take here we have to compute 1 upon so the domain of 1 by under the root of g of x, where our g of x is under the root of 2x, right? So you can think about this thing to be as a composition of functions. So first thing what we want g of x should be well defined. Okay, so g of x should be well defined. So when g of x is well defined, since it's an under the root function, 2x should be greater than 0. Right? So 2x greater than 0 means x should be greater than 0. Greater than or equal to 0. Because under the root function is well defined for equal to 0. So this is a one condition. So that means domain of G, we have x greater than or equal to 0. Right? Now, when does this 1 by under the root of gx will make sense? So since you observe here that what is the domain of under the root function? So if you consider f of x to be equal to 1 by under the root of x. Okay, so what will be the domain of f here? So first thing is this x should be greater than or equal to 0. That means x should be greater than or equal to 0. And x should not be equal to 0. Right? Because if x is equal, so ultimately x should be strictly greater than 0. That will be the domain of this f function. Is that clear to you?
Yes, ma'am.
Right.
Hello, ma'am. I
So
wanted
now,
to ask something. Hello.
yeah, just one second. So that means what we want here for g of x, we want g of x should be strictly greater than 0. But what is g of x? G of x is under the root of 2x. It's a square root function, and we know that square root function is always strictly greater than 0. But if you put x is equals to 0 here, this under the root of 2x will become 0. And for this, 1 by under the root of 2x, under the root of 2x, this does not make sense. Right? So that's why we just have to remove 1 point x is equals to 0. So that means overall, the domain will become x is strictly greater than 0. Is
Yes,
that
ma'am.
clear?
Got it. Yes, ma'am. Thank you, ma'am.
Okay. Yes, Lakshan.
Hello, ma'am. Actually, I have to give the end term exam only, and in the middle of the end term exam, I'm having my university end sem exam. So I wanted your help. So if you can guide me on which are the most important topic of the weeks which I should focus on to get a better score, because it will be very hectic month for me. So if you could.
What are the important topics? See, you have to do graph theory. That's a one thing. And since
Yes,
you
ma'am.
haven't learned graph theory yet, so I think that will be a little tough. It's not that tough. I mean, there the things are not complicated as calculus. Everything is precisely defined. So for NTEM, I'll say focus on graph theory more. That will be helpful.
Yes, ma'am.
Other than that, you will see questions from each week. So it's not the case that they have leave, but there will be much portion from graph theory. So one thing I can say, don't leave graph theory. So if you solve graph theory, then you can score 40% easily.
So ma'am, 40% is approximately the graph theory and the rest from the all the weeks, huh?
All of the weeks, but obviously in all of the weeks, these weeks 7, 8, 9 will cover more weightage.
Okay, so 1 to 4 are of least weightage, ma'am.
Least weightage. You will find out at most 1 or 2 questions will be there.
Okay, okay, ma'am. Thank you, ma'am.
Okay, so if you guys have any doubt, you can ask. Otherwise, you guys can leave. I'll be here for 10 minutes. And I'll put this PDF over the calendar as we usually do.
And week 7 graded assignment question number 10.
Okay. Question number week 7. So suppose company modify the error in estimation by algorithm 3 as c n dash is equals to n e to the power 1 by 20 n minus n. What will be the new error in estimation by algorithm 3 up to 3 decimal? So here you have to find out the limit of this particular sequence, correct?
Yes, ma'am.
That will be our idea. Now how to find the limit of this sequence? Let's see. Here we just cannot substitute the limit because as so this is the question. So here, so our c n dash is actually equal to n e to the power 1 by 20 n minus n, right? So how to find out the limit of this sequence? We have to think. So this is same as n of e to the power 1 by 20 n minus 1. Right? So but here what has happened? So cn. So as n goes to infinity, this 1 by n goes to 0. So as 1 by n goes to 0, this e to the power 1 by 20 n, that means this is going to 0. So that means this goes to 1. So here 1 minus 1 will ultimately this factor will go to 0 and this factor will go to infinity. So whenever we have such kind of behavior, we take it to be equal to 0 only, but let's try to decompose it further because the answer is not 0 in this case. So that means we have to adjust something and replace our limit by 1 by n so that we can do so. Okay. So what you have to do, you just have to modify this expression. So this is same as the cn dash. This is same as e to the power 1 by 20 n minus 1 and upon you can take 1 by n, right? Because this will jump to the numerator. So you can take this 1 by n into the denominator to make it 1 by right? N into 1 by n. So now here you observe here as n goes to infinity, we can look it to be 1 by n goes to 0. Right? So here we have now 0 by 0 case, correct? Because as 1 by n goes to 0, this will goes to 0 and this also goes to 0. So that means ultimately we reach to L hospital. So here the limit n goes to infinity cn dash is same as limit
Now I
1
can
by
solve.
n. Now you can solve, right?
Ma'am, last question number 6 of same graded assignment.
Okay. Number 6. Find the limit. So here I have discussed this. I guess this is the sum of odd parts. So wait a minute. 9, 15, 21, 6 and minus 3. So this is limit n goes to infinity of an of 9, 15, 21 plus and so on plus 6 and minus 3 upon n square is there. right? So what you have to do, here you observe, if you take 3 common, it will become 3 plus 5 plus 7 plus and so on plus 2n minus 1, okay, upon n square is there. Now what you can do, here you observe, here one remark you have to consider, that the sum of first odd term is actually equal to n square. N square. So that is the sum. That means 1 plus 3 plus 5 plus 7 plus and so on plus 2n minus 1. This is actually equal to n square. This fact you can actually easily prove. Either you can use the method of induction, or you will use this fact that the sum of all terms for sum of n terms is actually equal to n into n minus 1 by 2. So I'll leave the proof of this to you. Or else you can find the proof of this over internet. It's very easy. Okay. So you have to use this fact. So it will imply that this 3 plus 5 plus 7 plus and so on plus 2n minus 1, you can actually replace it with n square minus 1. Right. So this factor you can replace with n square minus 1. So this limit will now convert into very easy expression. This limit n goes to infinity. 3 is there, and here it will become n square minus 1 n upon n square. So this is same as limit n goes to infinity 3, and this is 1 minus 1 by n square. So this will goes to 0. So that's why answer is 3. So here one thing you have to do, you have to convert this factor into, this is the one result you should know. Is that fine?
Yes, ma'am. Thank you, ma'am.
Okay. Anything else?
No, ma'am.
This question has been asked to you many times. Just because I have only 4 days of this thing, and the last this thing I couldn't focus much. What is the thing that I have to really focus for this Q2 now? If I want to go.
See, you should be comfortable with differentiability, and I'll say domain of functions, composite functions. That's all, I guess. Because if you are comfortable with differentiability, you can handle limit continuity very easily. So overall, I'm saying just go through the whole 4 weeks. But no, see, basic differentiability is fine. Basic limit criteria also you should know. And that's all, I guess. Although you know how to find out the domain of function, right? One function, onto function. Main topic, one onto function, logarithmic. Yeah.
But I have to go back and focus on 1 to 4 again.
No. You should not go back. If you don't have time, then because there will be very less question from week 1 to 4.
Yeah, because
Or
we have
else,
5 days, right?
yeah. So one thing I can say, just go and have a quick recap. So if I was a student, then I'll have some notes, right? So just once, just read the main result, or read the methods what we have done so far, right? So that means how to compute transitivity, symmetricity, all those things. Yeah, how to handle polynomials and all those things, right? Just have a quick recap. Recap means just read it thoroughly once only. It won't take 1 or 2 hours, I guess.
Thank you.
Ma'am,
Yes, Madam.
this quiz 2 is not gonna have any eligibility or any stepping thing now in this course, because it's just a quiz.
Yeah, it's just a quiz, but I think it will give you some credits. So yeah, there won't be eligibility thing happening for quiz 2. You can give
Yeah,
it quiz
we
2.
don't have to stress that much now.
If you want the credit, then you have to. But see, don't bother that much, and just go and study whatever you have. That will be enough. At least go through the practice activity graded assignments questions.
Practice are very high. Graded are I even don't know. And activity I didn't did it.
Then you have to go stress a little bit.
नहीं मतलब अगर क्विज 2 में कोई भी ऊपर नीचे होता है तो उससे कोई इफेक्ट नहीं पड़ेगा ना, क्योंकि
उतना नहीं पड़ेगा, उतना नहीं पड़ेगा, थोड़ा सा पड़ेगा, थोड़ा सा, पर हाँ, थोड़ा सा तो पड़ेगा। अगर क्विज 1 में आपके बहुत अच्छे नंबर है तो नहीं पड़ेगा, बट नहीं है तो फिर थोड़ा सा।
क्विज 1 में पास हूँ मतलब मैथ में।
पास तो हाँ, फिर
मतलब 60 के आसपास थे, 61।
Madhav, the share goes
Huh.
like 20% from Q1, 30% from Q2, 40% from final, plus 10% from the graded asset.
Graded asset. And there is one more formula na, which take maximum of, I mean, we have two set of formula.
Yeah,
Whatever
if you
give
don't return
you.
either of them, yeah. Then if you don't return either of them, then only the total scoring is only for 90. It's not for 100, no?
Okay. Now for quiz 1 and quiz 2 also there is one thing. I mean, in one scenario they'll take maximum of quiz 1 comma quiz 2, or in another scenario they will take this 20 plus 35.
Oh, is it? Okay, okay. Because I thought the maximum thing, I thought it's only for people who don't attend either of the quizzes.
No. It's for everyone. They have computed. I mean, the last time they have did that formula. That's why I know.
All is well.
Okay, so thank you guys for joining. All the best for quiz 2.
Thank you.
Thank you.